record on this computer, share screen, rock and roll. Okay, there it is. All right, so last time when we left off, we were talking about the microcanonical ideal gas. Okay, and again, just to run through this real quick, again, microcanonical tells you a fixed constant energy. Ideal means no interactions. That is, the potential energy is 0 and we don't care about it, and the gas tells you that it is dilute. In other words, the total volume of the molecules is significantly less than the total volume of the container. So we have our box, we have atoms everywhere, atoms. The potential inside the box is 0. The potential outside the box is infinity. So in other words, we are never leaving the box. There's coronavirus out there, right? So we got to stay in the box to avoid the coronavirus. The box has a total volume of V, and we have N molecules in our box. Okay, and remember that we are looking at this box at a fixed constant energy, which we refer to as E naught. All right, so now because every possible arrangement of this gas that we're interested in has the same energy, that means that all possible states have the same energy. That is, every state in the ensemble has the same energy. Because we assume that the probability is a function of the energy, that means that every single state available to this gas at this fixed constant energy has the same probability. Consequently, if we want to calculate probabilities associated with this gas, then what we are interested in calculating are relative volume sizes in phase space. That is, how many states exist in a given region of the phase space. Okay, now, because the gas is ideal, as we talked about last time, the Hamiltonian is simply the total kinetic energy of the gas. There's no potential, and hence this is just equal to the sum of alpha equals 1 to 3n of p alpha squared over 2m. Again, we are assuming all the molecules are identical and have the same mass. We have 3 n values in our sum because we have n molecules and each one has 3 components to its momentum. And we wrote this as the big fancy p squared over 2m. All right. Now, if we just focused on one molecule, look at one molecule. Okay, if we write this out, then the energy is equal to just px squared plus py squared plus pz squared. So let me write it like that. And it's equal to this fixed constant energy. This is the equation of a sphere. Okay, so it's a sphere with radius equal to square root of 2m E naught. And so the phase space for this thing, you will recall, is a sphere. Sphere, there it is. Sphere. Voila, sphere. And so what we were interested in doing is if we take this sphere of radius 2m E naught square root, and then we kick the energy up a little bit to some higher value. Let's try this, shall we? So we kick the energy up by some small amount delta E. That gives us the shell. And so the volume in energy, the volume in phase space we're interested in calculating is the volume of this shell. Okay. And again, this is a simplification to just looking at one molecule. If we have n molecules, then we are looking at volumes. Oh, I don't like that one bit. Let's go back to my big fatter pen. So we're looking at volumes of spheres in 3 in dimensions. Okay, and this is going to come in handy. So once again, let me write down the general formula of the volume of a sphere in d dimensions. So that's what we called mu in d dimensions with a radius of r. This is equal to pi to the d over 2, r to the d over 2 factorial, or d over 2. All right, hilarious. All right, so we went through, we calculated, we showed how to calculate the density of states. That's this thing we called omega, and what we got for this was 3 n m times pi to the 3 n over 2 times the radius to the 3 n minus 2 over 3 n over 2 factorial, where the radius is equal to 2me square root. All right, so then what we were doing when we left off on, God, what day was that? Wednesday, was we were showing how to apply this reasoning to actually solving an interesting problem. All right, so the problem we were looking at was calculate the probability density for the x component. Just as a hint, it's not going to matter which component it is. We're just picking one and saying that's the x. We're going to generalize this when we're done. So the x component of the momentum of the first, and again, it doesn't matter which one's first, it's just whichever one you're looking at. The momentum of the first molecule is equal to some specific value. So it's equal to, what did we call this? We called this, we said that rho of P1 is equal to P1x. Okay, so this is, wait, no, that's not right. Hold on. So what we are, God, so we want to calculate the probability that the x component of the first atom is equal to some specific value, which we're going to call P1. And the question is, what is this? All right, and so again, if we go back to our reasoning about phase space volumes, so now what our phase space looks like, I'm going to call this Px, this is Py, this is Pz. Again, if we just think about one molecule of this gas, then let me do blue. Again, it's a sphere. Oh, baby, that is a good circle. Okay, so it is a sphere. There it is. Lovely. Okay, and again, so now what we're interested in is if the x component of the momentum has some specific value. So in other words, what we do is we start out here at the origin, we come up to some whatever specific value of the x component of the momentum it is that we're interested in. So we call that value P1, and then we just shove a plane through this sphere to take a section of it. Okay, so we come over here. I should do a different color. Let's do purple. So we come up here to this value. We shove a plane through the sphere at that value. And so what we're doing is we are taking a section of this thing. Let's see if I can do it. Okay, not too bad, not too bad. Where, okay, and so again, what we do is we come up to a value of P1 on that vertical axis. We just stick a plane through the sphere at that point, and so we're taking a section through that sphere. Now, again, what we do in order to calculate volumes is we take the energy that we're interested in and kick it up by some small amount. So we increase the volume of our sphere like so. And when we do that, that also increases the volume of this, or the radius of this section that we're taking, like so. And so now the volume of phase space, which corresponds to this particular molecule having this particular value of the momentum, is just the volume of this annulus here. It's an area, but an area is just, it's a volume in low dimensional space. So this is the volume of phase space with P1x equals P1. Okay, and then this, the volume of the shell, this is the volume of all states. Of all possible states. Okay, and hence, if we are interested in the probability of finding the, because probabilities are proportional to volume and phase space, then what we're interested in, if we want to know this, that the probability density that the X component of the first atom is equal to this specific value, then all we want to do is just look at the ratio of these two volumes. So it's the ratio of the volume of, well, let's not write, we don't need to write all that out. Volume, let's do it this way. Phase space volume with P1x equal to P1, and then we simply divide by the total volume. So total phase space volume. All right. Okay, cool. So now, so we talked about on Wednesday exactly how to calculate this. This is just this volume of a spherical shell in 3 dimensions. So we already know how to calculate the blue thing. What we're interested in doing today is to calculate the volume of the purple thing. All right, so now if this sphere is in 3 dimensional, is a 3 dimensional sphere, then when you take a section through this thing, you are reducing the dimensionality by 1. So in other words, the dimensionality of this annulus is equal to 3n minus 1. Okay. Hence, if we want, so what we want to do in order to calculate this purple phase space volume, okay, so what we need to do is to calculate the volume of a sphere in 3n minus 1 dimensions that corresponds to it having the energy E naught plus delta E minus the volume of a 3n minus 1 dimensional sphere with energy, with radius that corresponds to energy E naught. Make sense? Wunderbar. Okay, so now we need to know the radii that correspond to these particular energies. So we need to do a little bit of geometry here. All right, so now what I'm going to do is to, again, I'm just going to take this sphere I'm looking at here, and I just want to look at the XZ plane, okay? So let's draw the, so I called this PX and this was PZ. So in the XZ plane, the phase space is just a circle. And what we're doing is coming up to a specific value of the X component of the momentum, which we call P1. And the ring that we're looking at, the annulus, is just the ring that we get by sticking a plane through the circle right at that value, okay? So now what we're interested in is the volume of this ring. And so we need to know its radius. We need to know what this distance here is, which I am going to call R prime. Okay, so the radius of my annulus I'm going to call r prime. The radius of my sphere, remember, that's what I call r. Okay, or even more suggestively, let me draw that like this. That's r. Okay, so that radius is r. The radius of my purple annulus is r prime. Oh, and look, this is P1. So I have created here a physicist's best friend, a right angle. If it's not a right angle, it's a wrong angle. Very good. Okay, so now we just do some trig in order to determine what r prime is in terms of r and P1. Okay, and you know, you guys are smart. You can just look at this and you can see that, let me switch back to purple, r prime is equal to r squared minus P1 squared square root. The Pythagorean theorem, yes? All right. So now this is the radius of our annulus with energy E naught, where again, I will remind you that R is equal to 2m E naught square root. Whew. Okay, everybody good? Very good. All right, so now let's do it. Okay, so now just like the argument goes on that we made on Wednesday, the way that we're going to calculate this, again, so we, so what we're looking at is the volume of a 3n minus 1 dimensional sphere that corresponds to energy E naught plus delta E minus the volume of a 3n minus 1 dimensional sphere that corresponds to a radius with energy E naught. And then if we divide this by delta E and take the limit as delta E goes to 0, this is a derivative. So we're going to take the derivative of a 3n minus 1 dimensional sphere with a radius. So I guess the technically correct way to write this is that it is a functional of the radius, which is a function of the energy. All right, so that's what we're doing. So now you go back to this formula I reminded you of right here. So our general formula for the volume of a d-dimensional sphere, and we plug that into here with a dimensionality of 3n minus 1. All right, so here's what we're going to do. So let's do it. So we're going to take the derivative with respect to energy of the volume of a 3n minus 1 dimensional sphere, which is this, pi to the 3n minus 1 divided by 2 times our radius, which is 2me minus P1 squared. So that's our radius, right? Well, radius squared. And we raise this to the power of 3n minus 1 over 2. And then we divide by this freaky factorial. So our freaky factorial here is 3n minus 1 over 2 factorial. So that's what we got to take the derivative of. Again, it's not, you know, it's a little ugly because you got, you know, you're taking the derivative with respect to energy and you got the energy here inside this quantity. So you got to apply the chain rule a couple times. But other than that, all you got is a bunch of crappy constants and piece of cake. Okay, so if we do this, what we will get is, I'm going to do it in excruciating detail now, okay? So what we will get is pi, the 3n minus 1 over 2. So that, again, it's just a constant. Divided by factorial, 3n minus 1 over 2 factorial. All right, from taking the derivative of this quantity, we are just, you know, just pull down the exponent. So the exponent is 3n minus 1 over 2. Then the chain rule says you got to take the derivative of the thing that is inside the quantity. So you got to factor a 2m from that. And then we get our quantity back here, 2me minus p1 squared. And that is 3n minus 3 if you do the algebra, like so. All right, and we can do a little bit of algebraic massage and clean it up a little bit, and what you get is this, pi 3n minus 1 over 2 r prime to the 3n minus 3 divided by 3n minus 1 over 2 factorial, where r prime, I will remind you, is 2me minus p1 squared square root. Okay, so that is our annular volume of phase space. Okay, everybody cool? All right, so this kind of hairy looking thing is this purple, it's the numerator of our probability, right? The similarly hairy looking thing we calculated on Wednesday is the denominator of our probability. And so to calculate this probability density, all we do is we take this volume we just calculated here, and we divide it by the volume that we calculated on Wednesday. And so if we do that, here is what we get. Okay, hence, rho of P1x equals P1 is equal to 3n minus 1. So I'm just going to, you're just writing the exact same thing over again. It's exactly what we wrote up there. Over 3n minus 1 over 2 factorial. Okay, so that's the purple volume. And then the blue volume is the similar thing we found on Wednesday, which is this, pi to the 3n over 2 r to the 3n minus 2 divided by 3n over 2 factorial. Okay, so there's the answer. Voila, it's magic. Okay, but now the problem is again, this isn't very illuminating, right? So we need to massage this a little bit to get it into a form which is comprehensible by the human mind, all right? So the remainder of what we're going to do to this is just algebraic manipulation just to make it look prettier, okay? So now the first thing I point out to you is let's look at this. So this 3n, well, that's a constant, right? M times pi, that's a constant. And this is a constant. And this is a constant. And this is a constant, right? So we got a whole bunch of constants times some ratio of my radii here. So what I'm going to do right now is I'm going to get tired of writing down constants. So I'm just going to, for the time being, forget about the constants, because we're going to be able to get the constants back easily at the end anyway, because we know this thing has to be normalized. So let's just forget about the constants for now and say, so forget constants. Okay, so what we're going to do is we just note that this probability density we're interested in is proportional to, so if we just write down this ratio of radii, what we get is r squared over r prime cubed. So that's coming from these parts of the exponent times r prime over r to the 3n. So let's just look at that and try to make this a little bit more comprehensible, okay? All right, so now follow me on a mathematical journey, shall we? So first of all, let's remind ourselves that r prime squared is just equal to r squared minus p1 squared. Okay, so now I just massage this a little bit. I just divide by r squared, and I get this. So it's 1 minus p1 squared divided by r squared. And whoops, what the hell were you writing there, Professor? P1 squared over r squared. So this is P1 squared, and remember that r squared is 2me. All right. So in other words, r prime over r is equal to 1 minus P1 squared over 2me square root. Okay. And now I raise everything to the 3n power in order to make it look like this thing. Okay, so if I just take this quantity, raise it to the 3n power, then what I get is this part of my probability density. All right, so here's what we get. Okay, so we get that our probability density is proportional to r squared over r prime cubed times 1 minus p1 over p1 squared over 2me to the 3n over 2. Okay, everybody cool? Okay, now let's use one of a physicist's favorite little tricks. All right, so let's look at this thing that we just manipulated here. So let's take a closer look at this. So we have 1 minus p1 squared over 2me to the 3n over 2. And I will remind you that n is a tremendously large number, right? So n is gigantic. It's like 10 to the 23. Okay. So in other words, if this quantity inside these parentheses is anything, even just a fraction, little bit smaller than 1, it is very quickly going to completely vanish. All right. So in other words, this quantity here better be approximately equal to 1, or else we're going to get a probability of 0. Does that make sense? Okay, so now in order for that quantity to be approximately equal to 1, that means that this quantity, p1 squared over 2me, must be very, very, very small, right? So typically, small quantities in mathematics, this is what you call epsilon. So we're going to define that to be epsilon. So in other words, what I have is 1 minus epsilon raised to a tremendously large number, where epsilon is very, very tiny. Okay. All right, so here is one of the physicist's favorite tricks. So 1 minus epsilon, that's the same thing as 1 minus epsilon plus epsilon squared over 2 minus epsilon cubed over 3 plus epsilon to the 4th over 4, so on and so forth, if epsilon is very small. So if epsilon is very small, then you'll neglect these terms anyway. And so now I ask you, what is that the Taylor expansion of? Anybody? Bueller? No? That is e to the minus epsilon. Okay? So in other words, we are going to say that 1 minus p1 squared over 2me is approximately equal to e to the minus p1 squared over 2me. So anytime you ever see 1 minus a tiny, tiny number, you as a physicist should say to yourself, oh, that's the same as if I just make that the exponential of that tiny little number. Okay? Okay, so then what we have is that 1 minus P1 squared over 2me to the 3n over 2 power is the same thing as e to the minus P1 squared over 2me times 3n over 2. Cool, right? All right, so that takes care of this part. Now let's talk about this part. So let's look at the ratio of r squared over r prime cubed. Okay. Now, what we're going to say is that as delta E goes to 0, and again, if you go back and you look at our drawing of phase space here, then as delta E goes to 0, what you're going to get is that these things are approximately the same. Okay, and so what we're going to say is that this is approximately just 1 over r. It feels like cheating, right? But that's what physics is, it's cheating. Okay, so this is 1 over root 2me. Okay, so to summarize, let's combine these two results. So finally, we have that this probability density of one of the components of our momentum of one of our atoms is equal to some specific value is proportional to 1 over root 2me e, well, let me write it like this, exponent minus P1 squared over 2me times 3n over 2e. Is that right? No, sorry. I have an extra e in there. It's that. All right. So now, what is this? That's a Gaussian, right? So if you guys have ever heard of the central limit theorem, have you ever heard of the central limit theorem? That is, regardless of the probability distribution that you're looking at for some random quantity, if you look at enough samples of that random quantity, it's going to look like a Gaussian. And it's exactly the same argument that you run through this thing, you get that your probability is proportional to 1 minus some small number, and by making this approximation, the thing winds up looking like a Gaussian. All right, so our probability density is a Gaussian. To make it a probability density, then we need to normalize it. Okay, so let's normalize this thing. All right, so this quantity here, I'm going to say that in order for this thing to be normalized, I have to multiply by some constant. So what I'm going to do, here's what I'm going to do. I'm going to make this an equal sign. And then let me put a prime on it just to be pedantic. I'm going to say that the real probability distribution is equal to this thing we just calculated times some constant integrated over all possible values of dp1. And you say that this has got to be equal to 1, right? That's normalization. So by taking this, sticking it in here, you can determine what this constant a has to be in order for the thing to be normalized. And it's just, you do a Gaussian integral. I'm not going to bore you with that. And so here is what you get. Here is the final answer. Is equal to this, 2 pi m times 2e over 3n square root. So that's our normalization constant that we would get from doing this integral times our exponential. Like so. So that's our answer. Ta-da! That's what we're after. Okay, so now notice that this is kind of amazing, right? All we did was just count things, right? All we did was just calculate volumes in phase space. And essentially all that volume corresponds to is it's proportional to the number of states that correspond to the situation that we're looking at. And simply by counting states, we are able to determine this probability distribution in terms of N, E, and the mass of your particles. Okay, so you have, you got this box full of God knows how many molecules, and simply through this reasoning of just calculating areas in phase space that correspond to the energy that you're interested in, you can calculate probabilities explicitly in terms of just these three observable quantities. All right, so in other words, we did magic. All right, and we did magic to get this thing in terms of quantities that we can measure in the lab. So in other words, we can experimentally test whether or not this thing is correct. And of course it is, so otherwise why would I be telling it to you? All right, so now let's talk about this thing and what it means. All right, so let's notice
question.
Yes, please.
You said that it is correct. Is there a limitation to how correct it is, depending on how small or how big?
So this is correct in the when you're looking at a system that is in equilibrium at some fixed energy with the assumptions that we made previously. That is that the masses of all, in other words, it's a monatomic ideal gas. So if you start making things more complicated, that is like diatomic gases, and where it's not ideal, that is where the atoms and molecules interact with one another, that's going to start introducing some corrections to this. Okay, but it turns out that even then, this is still a very, very good approximation.
All right, thank you.
Okay, all right. So let's note some features of this thing. All right, so one of the things we're going to start doing next week is start talking about temperature. All right. So now it turns out, so again, we'll start talking about an ideal gas, and we will define something called temperature. And we will be able to calculate, if I give you a monatomic ideal gas of energy E, what would be the temperature that you measure. All right, and I'm going to tell you right now that what I am going to show you in a few lectures is that the temperature of a monatomic ideal gas is directly related to its energy, and it is given by this. So it's 1 over some constant, where this constant is what's referred to as Boltzmann's constant. And so it's 1 over Boltzmann's constant times twice the energy divided by 3 times the number of molecules. Okay, notice this is exactly what shows up here. Yes? Okay, so in other words, 2E over 3N is equal to KB times the temperature. So another way we could write this probability distribution is like this. right? Because all I did was just replace 2e over 3n with 1 over kt. Okay, now notice that this p squared over 2m, that's our kinetic energy, right? So in other words, this exponent is just a ratio of kinetic energy of your gas divided by thermal energy, essentially. Okay, so now this 1 over kBT, this shows up so frequently that you get tired of writing it over and over again. And so we give it its own symbol. We call this beta, which you will hear referred to as the inverse temperature, or I will refer to it as the laziness factor, again, because you just get tired of writing 1 over kT. So in other words, you've got that our probability density is equal to 1 over 2 pi m, I believe now this is over beta, e to the minus. So now what this is the Hamiltonian, right? Our Hamiltonian was p squared over 2m times beta. Okay, so this is the Boltzmann distribution, right? This is the famous Boltzmann distribution. This thing right here is what's referred to as the Boltzmann factor, or the Boltzmann weight. And so this argument that we went through in order to derive this, again, it's going to be really general. The where this Boltzmann weight came from is this assumption that we made right here. All right. And regardless of the details of the system that you're looking at, or like its mass and so on and so forth, pretty much any time you go through an argument about any system, you're going to wind up with something that looks like this. Again, this is like the central limit theorem showing up again. And so, in other words, probabilities, it's always are a very good assumption that any probabilities that you're talking about are going to be proportional to this Boltzmann weight of whatever state it is that you're interested in. Okay, another observation. Okay, I believe in your homework, we asked you to calculate the average kinetic energy of a ideal gas. And what you get is 1/2 kT. Okay, and so you get that it's 1/2 kT in a given dimension. All right, and so the net kinetic energy is, you have 3 dimensions, and so I guess actually this is more technically correct. So the average kinetic energy that you get is just the sum of the 3 components of your momentum. So you get 3/2 kT. All right. In other words, your x momentum carries kinetic energy 1/2 kT. Your y kinetic energy carries 1/2 kT. And your z kinetic energy carries 1/2 kT. So each dimension has exactly the same fraction of the kinetic energy in it, essentially. This is what's referred to as the equipartition theorem. Okay, so the equipartition theorem essentially just says that it doesn't matter which direction you're looking in, they're all going to have the same fraction of kinetic energy in them. I have to remind my wife not to text me while I'm teaching in the future. Okay, and I think that's about it. That's all the important things I wanted to say. So what we did was just derive the Boltzmann distribution just by looking at ratios of volumes in phase space. Pretty crazy, right? All right, so does anybody have any questions about anything? All right, very good. Then we will come back to this on Monday and start, as I promised, talking about temperature and also what happens when you don't require the total energy to be fixed. That is, we relax our assumption that we are in the microcanonical ensemble, and we will see what happens on Monday. All right, so have a good weekend. Don't catch the Rona, and I will see you on Monday.